Trying to see who is online.
Dude just had his camera pointed at the ceiling.
That's the best place to point it. Here, do you want to see them again? There. Hello, online people. Wave to the class.
Hi, Jake ceiling.
Thanks, guys. Look it. We're like a happy family. All right, let's get started. Like I said, I don't want to teach the whole hour because topic one is a little meaty. So I'd like to give you some time in class to work on topic one because, again, I think there might be some struggles there. And it's probably better off if you have a chunk of time during class so you can maybe ask me some questions. That homework assignment's going to be due on Tuesday, okay? So next week, Tuesday, by midnight, homework topic one is due. It is one of the bigger assignments I've probably given you all year. So side note, there's a decent amount of stuff there. But again, I'm going to get through 5.4, and then we'll give you a chance to work on that for the remainder of the hour. 5.4 is different. The math is gone today. Okay, this is more conceptual stuff with kinetics, and we'll tie in the math stuff again as we go forward. But 5.4 is on what's called elementary reactions, and I'll explain what that is. So let's go. All right, this is review. I'm sorry, there's a smidge of math. But do this if you could. I'd like you to give me a rate law from this data. This is 5.1, 5.2 stuff. Okay, so look at the data table here. Figure out what the rate law is from this data set. Go for it. I'll give you a head start. And feel free to talk to each other if you're in the room.
I slept good last night, the first time. At 9. Yeah, it's not normal. I do it around the middle. So, plus I kind of had headaches. Pretty close to everyone.
All right. Now, again, I'm just being a little annoying, right? Here's the deal. We can kind of assume that this is close enough to being constant, right? Like I'm hoping that maybe your brains were thinking the same thing. Obviously, 3.9 and 4.0 are different values, but they're really, really close. And I don't know if it's worth the mental angst to just treat it as it not being constant. I'm going to treat that like it's constant because it's close enough. You know what I mean? The reason why I did this is because, like, your data's not always perfect, so it is what it is. But yeah, it's close. It's really close. I'm not going to lose sleep over it. So let's just say this is constant. All right. So from trial 1 to 2, the molarity of our fluorine tripled, or the rate, I'm sorry, was up at the same factor, and in this instance, it's 3 to the first, right? Why did I write 2? Great question. guys ask such good questions. I don't know. Just brain's not working. All right. Now, the other ones, again, we could look at trial 1 and 3. Again, they're not like next to each other in the data table, but they're all independent. So who cares? Right? So let me look at from trial 3 up to trial 1. Because if I go from trial 3 to trial 1, the molarity of NO2 is more or less doubling. Again, it's close enough where I'm not going to, overthink it. And this is constant. So from 3 to 1, that doubles. What happens to the rate? We'll go all the way around. Same thing. Okay? I think, based on what I'm seeing, and I hope you agree, that both of these are first order. Disputes? Questions? Sleepily nodding your head? That was a little too emphatic, but okay. Deal, I guess. Rate equals K multiplied by NO2 to the first, F2 to the first. Do I need the ones? No, I don't, but whatever. Okay. That's old news. I hope that's easy. Again, every time you get one of these data tables, it's going to be just slightly different, which can be annoying, but take your time. Each trial is independent. Again, try to isolate the variables if possible. It's not always possible, but we'll try our best. Okay, so oftentimes,
Why don't you define K?
what do you mean?
Like, is that just a whole rate? You don't need to define K?
Well, I might need it later or something. I didn't ask for it right now. But yeah, we could have, I could. And if you did, I might use it later. I forget if I need it or not. Maybe I do. Maybe I don't. But if they don't ask for it, you don't need to solve for it. I just wanted to set up for right now. We could though. All right, so oftentimes chemical reactions do not occur in one single step. Okay, this is a big misconception or a big misunderstanding until you learn about it. But it's pretty rare that a chemical reaction occurs like all at once, one step, done. Okay. For example, it's highly unlikely that this reaction, NO2 plus F2, occurs in one step, where 2 molecules of NO2, let me go back for a second. Okay, here, this is the reaction I'm talking about, right? This one right here. Okay, it's unlikely that I have 2 of these molecules and one of those molecules all traveling around, and they all 3 of them hit and collide at the same spot at the same time. Okay, that's pretty unlikely. It's unlikely that 3 things all collide at the same instant in time. Okay, so as a result of that, it more likely occurs in a series of steps. Okay, the more likely scenario is, instead of having 3 molecules all smack into each other at once, what happens is two molecules smack into each other, create something, and then a third one comes in and smacks it later in a series of what are known as elementary steps or elementary reactions. Okay, that's much more likely. Hear enough to try to I need to hear more. That's a joke. We get along really well. Okay. Where was I? What am I saying? All right. So it's unlikely that this reaction with 3 reactant molecules, right? 2 NO2s and 1 F2, it's unlikely this occurs in one step. It occurs in a series of steps or multiple steps. And the series of steps we call elementary reactions or elementary steps. Okay. So a more likely scenario looks like this, where I have one reaction occur, and then I have a second reaction occur. And the total, right, if I were to add this up, would be 2 NO2 plus F2. Okay, now careful, right? You see how this shows up on both sides? That would cancel, right? And then I have 2 NO2F. So that's the same reaction that was on the previous slide, but instead of implying that it happens in one step, in reality, it probably happens in a series of steps. Okay? That's what today is all about. It's all about analyzing and looking at the multiple step process that occurs for a lot of chemical reactions. Okay? Now, the hard part is each of these individually looks like a chemical reaction, right? However, they don't occur individually. They occur in sequence to produce the overall reaction, right? This is the overall reaction, the one that we care about, the one that we're interested in. It's just that it happens in multiple steps. Any questions so far? Am I making sense? Okay. The main question you might have is, well, why, right? The why is that it's very unlikely that three molecules all smack into each other at once. It's much more likely that two molecules collide, create something in the middle, and then another two molecules collide and create something else, right? That's a much more likely scenario to have only two things colliding as opposed to having three things collide. Okay, so we call these elementary reactions or elementary steps. I will more often call them reactions, I guess, but the likelihood of that three separate molecules colliding at the same time at the same spot seems like it might be possible. Okay, in reality, it can happen. It is possible that three molecules can all collide at the same point at the same time, but it's just not very likely. Okay, not going to happen in most reactions. So the concept of why chemical reactions often occur in elementary steps is more clear when we look at the next example. Let's look at this one. Balance that if you could. Shouldn't take you, hopefully not too long, but balance that if you could. You done? 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens. 6 plus 4 is 10 oxygens, 10 oxygens. Right? Nothing weird, no 0.5 method, nothing funky going on. Hopefully that wasn't too bad. But let me give you the same scenario I just gave you for the previous reaction about this one. What I had previously said is, how likely do you think it is that three molecules all smack into each other at the same time at the same spot? Not very. Okay, well, if that's not likely, then how likely is it that 6 molecules all smack into each other at the same time at the same spot? Okay, quite literally not possible. Okay, we've approached 0, right? This is like one of those probability limit situations where we've effectively reached 0. This is not going to happen. You're not going to have 6 molecules flying around in space all collide at the same instant at the exact same spot in time. Not going to happen. Okay, so here's the issue though, right? Does this reaction occur? Okay, well, let me give you some context. This is propane. This is oxygen. We're doing combustion, right? This is propane gas. That's what's in your grill if you have a gas grill at home. Okay? So does this reaction happen? Can you burn propane? Yeah, absolutely you can. Now, are 6 molecules going to collide at the same time to make this happen? No. It's going to happen in a series of elementary reactions or elementary steps. Okay? So this is a weird thing, like I said like 10 minutes ago. We don't really talk about this in regular chemistry or early on in chemistry at all. But the deal is that most chemical reactions don't happen in one step. They happen in a series or multiple steps to give you the overall balanced process. Okay? What more likely occurs is one oxygen comes in and bonks into the propane molecule and starts it. Then another one comes in, bonks into the remainder of that, and another one comes in, right? And effectively, the big propane molecule just gets hit with oxygen molecules individually, and then the overall net result of that process gives us this balanced reaction. So it's probably 5 steps. That's probably a 5-step elementary process for this overall process to occur. Okay? And again, the reason why this is the way it is just, you know, probability. It's highly unlikely that more than 2 molecules can collide at the same spot at the same time. Highly unlikely. And we need a collision in order for reactions to happen. All right, so when reactions are broken apart into their elementary steps, we can analyze the rate of the individual steps to determine the overall rate law. The elementary step that occurs the slowest is called the rate determining step. Basically, the whole process can only go as fast as the slowest step. Okay? If the whole reaction is 5 steps, one of them is going to be slower than the other 4. That's just, that has to be that way, right? Something has to be the slowest. So if I have a chemical reaction that occurs in 5 steps, one of those 5 is the slowest step, and what it gets called is it's called the rate determining step. The overall process can only go as fast as the slowest step. That makes sense, right? You couldn't go faster than the slowest one allows you to go. So it's called the rate determining step. We use the slowest step to figure out how fast the overall process can go, because that's the one that limits the rate. Okay? So a couple things. When the slow step is identified, all right, and I'll go back way back to the beginning here. Okay? You may have noticed this, right? Slow and fast. Okay? With elementary reactions or elementary steps, most of the time they write in slow and fast next to the arrows. Fast is just generically saying it's not the slowest. It doesn't mean that it's actually fast. It just means that it's faster than its other elementary steps, right? So if I had 5 steps, 4 of them would say fast, 1 of them would say slow. There's no quantification, right? There's literally no numbers. Fast and slow can mean different things in different reactions. All we're trying to do by saying this is we're trying to find the slow one, because that's the one we need to look at. That's the one we need to focus on. Okay? With elementary reactions, the slow step will determine the rate law. And it's really easy. Okay? Here are elementary steps. These are fake elementary reactions. Okay? If this were the slow step in a multi-step process, the rate law would equal K multiplied by A to the first. The reactants of the slow step will match the rate law. The reactants of the slow step will match the rate law, the equation. Another example, A plus B. These are the reactants. This represents a slow step. So the rate law should look like whatever the reactants are. Go ahead, do the next 4. Your reactants, they turn into the rate law, or rather, I should say, the slow step of a multi-step process. The reactants will match the rate law. Sorry, just getting set up. Okay, this is the slow step. Slow, elementary step. These reactants must match my rate law. A to the first, C to the first, C to the first. Here's my slow step. This must match my rate law. I have two A's, so what should I do? That. Hopefully that's pretty logical, right? Suppose you could write it out as A times A, but you know, that equals A squared. So I hope that makes sense. Two B's. Well, that's the same as this, isn't it? Just written a different way, right? Then last but not least, we have that. Now, we'll talk about something later next week called reaction mechanisms. Okay, and I'll discuss more of this when we get there. But what's really important to understand is that when chemists are trying to decide how a reaction occurs in multiple steps, okay, they have data before they try to determine the multiple steps. Okay, if that doesn't make sense now, that's fine. I will talk about that a lot next week. All right, I'm almost done, actually. I don't want to teach too much more. Okay, this is just a vocabulary slide, basically. There's a couple terms that get used when talking about elementary steps. So blank is defined as the number of species that must collide to produce the reaction. This is called molecularity. That's not spelled right. Molecularity. There you go. Okay, so molecularity describes how many molecules are smacking into one another. Name a reaction that didn't need a collision, but just involved a single molecule. Okay, this is called unimolecular. This, of course, meaning one. Name a reaction where two molecules collided. There's like two choices, right? I think we've had like two prefixes that are applying the number two. Which one you want? What? Huh? You're wrong. Okay, it's bimolecular. I know. Annoying because, yeah, we've literally used di or bi as a two prefix, right? Name a rare reaction where three molecules collide at the same spot at the same time. Unimolecular, bimolecular. It's a great guess, but it's not right either. It's termolecular, which is really annoying. I feel like it should be tri, but it's ter. Tertiary, I don't know. Maybe that's again, it's dumb. I just teach things. So blank collisions always give a second order overall rate law. So these are the different types of collisions that can occur. All right. If it's unimolecular, that means one molecule is just breaking apart, right? Nothing collided with anything. One molecule breaks in half. Decomposition, basically. If two molecules smack into one another, that's called bimolecular. And if three molecules smack into each other, it's called termolecular. Now, what do you get if two molecules smack into each other? You get whatever the order is. If one molecule is all by itself, this is unimolecular, first order. This is bimolecular. There's two of them. It's second order. Termolecular, 3. Bimolecular, 2. Bimolecular, 2. Trimolecular, or termolecular, I said it wrong. 3. Okay, so what collisions give a second order? Bimolecular collisions. Which leads us to 5.5. I don't want to teach that today. Okay? I would like you to work on your very first assignment. None of this stuff that I just talked about is on your first assignment. Your first assignment covers 5.1 through 5.3. Please spend your time right now working on it. That goes for you at home too. I'm going to let you go, but I can't strongly recommend enough that you should spend the next half an hour just at the very least reading through what you need to do on homework topic 1 and start trying to figure it out, especially the backside. The backside's a little tricky, okay? A lot of it deals with yesterday's stuff on the backside of that sheet. So please give it a shot before you pack it up for chem for today, okay? So you're free to go. Have a lovely day online, folks. Thanks for your attention. We'll pick this up next week. People in front of my face, please talk to each other. Work together. I'll walk around and help you out too. You got a huge advantage because I'm right in front of your face as opposed to those people. But please work on homework topic 1. Yes, Dylan?
Is there such thing with four molecules? Would that be called?
To the best of my knowledge, that doesn't happen ever. So if it were named, I don't know what it would be named. I don't know what that prefix would be because the other ones were fighting us a little bit. So I was going to say tetra, but I don't think that's right either. Since they use the prefix ter, maybe it would be like quat, because like quaternary, like whatever that quaternary structure. I don't know. But again, it's not really applicable because it's not a real thing.